chapter where Professor Kaspi will be coming from Canada. So very pleased that we have Vicky Kaspi coming from McGill to visit us and talk to us today about Millisecond Pulsars. She started out at McGill, where she is currently. She then got her PhD at a small university near here in Princeton, called Princeton. She then was a Hubble Fellow at Caltech, moved to MIT, and then decided to go back north, where she joined us. She is knowledgeable about all things millisecond and pulsar, about which she's going to tell us. She also has numerous awards, which I'm not going to list most of, but notably in 2010, she was elected to the National Academy and the Royal Society in the same year of London. So, both sides of the land. We're very happy to have her, and stay warm, and thank you, Vicky, for joining us.
Okay. Well, thank you so much for having me here. It's a thrill, and I've really enjoyed my brief stay here so far, interacting with a lot of you. Today, I'm going to tell you about the hunt for millisecond pulsars. Something I really enjoy doing, something that's really fun, and I hope by the end of the talk you'll understand why I love spending so much time doing this. Here's an overview of what I'm going to talk about. I'll first give you an introduction to radio pulsars, hoping to put everybody on the same page with these remarkable objects, what they are, and then try and motivate. Why do you want? We actually know of about 2,500 of them in the Milky Way galaxy. Why do we want more? Why is it important to try and find more of these objects? And I hope I'll convince you of that. And then I'm going to describe how we go about doing it. A very interesting, intellectually challenging problem to find them, big data, high-performance computing, supercomputer problem, and I'll describe why that is and how we go about doing it. And I'll describe some current pulsar surveys, these clever, really ugly acronyms, PALFA and GBNCC. I'll explain what those surveys are and give you some discovery highlights. We've been making quite a few discoveries, in some cases very unexpected results, things we were not actually looking for, but there they were. And if I have time in the end, I'll tell you about a new radio telescope, CHIME, that's being built in Canada, something that we're very excited about. I might not have time for that, but if you want to know more about that and I don't get to it, you can ask me later. So in the interest of putting everybody on the same page about radio pulsars, what is a radio pulsar? Well, first, it's important to understand that stars, like our own sun, or stars in particular more massive than our own sun, have evolved with time. They change, and they're born in this, in giant molecular clouds. And they really the fate of a star, of a hydrogen burning star, can go in two different directions depending on the mass of that star. And so for low mass stars, typical mass stars like our sun, the fate is here's the sun, eventually it turns into a red giant, and goes through an interesting planetary nebular phase and ends up as a white dwarf star. And those are very interesting, supported by electron degeneracy pressure, and there's lots of people who could tell you all about white dwarfs. I'm not going to talk about those today. On the other side, for the more massive stars, and exactly, I'm not quantifying for you exactly what I mean by more massive. There's people typically say 8 times the mass of the sun, 10 times the mass of the sun. Those go to a red supergiant phase and eventually undergo a core collapse supernova explosion, in which case 2 possible fates exist. One is that the most massive objects form black holes, and the other is the intermediate mass objects form neutron stars. And it's these neutron stars that I'm concentrating on today. These are, I'm going to tell you more about them. They're degenerate objects supported by neutron degeneracy pressure, not quite collapsed to the oblivion of a black hole, hovering on the verge of that collapse. So these are very dense objects that have very extreme properties.
Question.
Yeah.
What is this time scale?
Yeah.
Is it pretty much an average time scale, or is there a large distribution?
Yeah, no. So the star's lifetime before it collapses to one of these types of compact objects depends strongly on its mass. So the lower the mass star, the longer the star lives, actually. So the time scale for this to happen can be, many hundreds of millions of years, a billion years. The time scale for this to happen, the massive stars die out really fast. And so the time scale for like a 50 solar mass star to collapse can be 1 million years, something like that. The neutron star is sort of intermediate, then we're talking, maybe 10 million years, something like that. So now, neutron stars, one form of neutron star. This is one form. We think not all neutron stars are radio pulsars, but the observable, the most easily observable class of neutron stars are these radio pulsars. These are rapidly rotating, highly magnetized neutron stars. And the picture that you're seeing is sort of a cartoon, how we understand how we observe these objects. Here's the neutron star, and this is obviously a very cartoon version, but has some rotation axis that's vertical in this direction, and then some magnetic axis that is misaligned with the rotation axis. And we believe that there's these beams of radiation that are coming out of the magnetic axes, and of course there are very detailed models for how this comes about that I'm glossing over, and if you're very interested, we have experts right here, Andre Gruzanov, who can tell you all about this sort of thing. But the point is that what we observe here on Earth is one flash of a beam if it manages to cross our line of sight from this vantage point in the galaxy. So you could see if you went to another planet somewhere else in the galaxy, you might see a different sky of pulsars, just because some would not be clearly here, some are just not viewable because of this beaming effect. And of course, these are compact objects that I'm going to describe. The radius of a typical neutron star is about 10 kilometers, which across interstellar distances is very, very small. And so we don't actually ever resolve this picture. This is a cartoon. What we really do observe is just the variability in time of a signal from a telescope. So we see it's time series analysis that we're doing. So for radio pulsars, as I said, there's about 2,300 known, and nearly all in the Milky Way galaxy. We do know a few in the Magellanic Clouds. But these are generally very faint sources, and it's very hard to detect them in external galaxies. We think maybe with the next generation of radio telescopes we'll be able to do that, but today we can't. And we talk about radio pulsars because due to some quirk of nature we don't fully understand, they love to produce radio emission. As I said, they're most easily observed in radio waves. But they actually do emit across the full electromagnetic spectrum. They're also fairly commonly observed in X-rays and in gamma rays. But typically we see something like 100, maybe 150 objects at those high energies. The vast majority of neutron stars we know about are observed exclusively at radio waves. And so that's what I say, generally most easily observed in the radio band. Now, what do we actually observe? We observe like I said, a time series of pulses, and we refer to the pulse period. P is the time between successive pulses. And as I say, they're very, very faint. We typically, to detect them, we need very large radio telescopes, like the 100-meter aperture here in Green Bank, West Virginia. This is a Green Bank telescope. You can see here the aperture. This is a building here, and there's a car down here somewhere. It's very hard to see, but you see it's a very, very large structure, and that's what we need. We need these large collecting areas. And so this is actual data from the GBT telescope for one radio pulsar, and this is an extremely bright radio pulsar where you can actually see the individual pulses. For the vast majority of radio pulsars we know about, the pulsars, the individual pulses are below the noise, and we need Fourier techniques to detect them. So just some basic neutron star facts. Neutron star mass is, these have been very well measured, and generally they're around 1.4 solar masses, which, if that's not very intuitive, what a solar mass is, it's about 500,000 Earths, so I hope that helps you. The typical neutron star radius, as I said, 10 kilometers, and this is, just to set the scale, I'm from the island of Montreal. Montreal's an island, and here it is, and if you brought a neutron star there, this would be about the size of the island of Montreal, and there's McGill, if you're wondering where in Montreal it is. They also, so you have to realize you have 1.4 times the mass of the sun crushed into a sphere of radius 10 kilometers. This is very, very dense matter. So if you went to a neutron star, which I don't recommend, and you took a teaspoonful of that matter, it would weigh 1 billion tons or something like that. So this is collapsed, dense matter. There's no, the nucleons are all crushed together. And so you have these very high densities, and on top of that, they also spin very, very rapidly. So I showed you a picture, a cartoon of the rotation. In that case, it was, a few hundred milliseconds was the period. The fastest pulsar that we know of rotates 716 times per second. Okay, that's a millisecond pulsar, and sometimes late at night, I wonder, I should just say that 716 times per second, that's as fast as a blender. just to set the, so give you a physical intuition for how fast these stars are rotating. And late at night doing Google searches, I wondered if the fastest pulsar we know of, the 716 hertz guy, which, by the way, we discovered at McGill University using McGill supercomputers, is that the fastest blender on Earth? And I just thought I'd mention that the fastest blender on Earth, at least according to my Google search, is this Vitamix 5000 that maxes out at 625 rotations per second. So pulsars beats blenders.
I think there are lab blenders that crush that.
Yeah, so yeah. Thanks, David. I appreciate that. I've given this talk, public talk. This is just a couple of slides from public talk just by way of introduction, and I always get the biologists going, our centrifuges are faster. And I say, okay, we're working on beating the biologists next. Now, you might wonder... you might wonder, what is the speed at the surface of a millisecond pulsar? And this is just a simple calculation to show you that these things are very extreme in many ways. If you just take the velocity is 2 pi r over the spin period, and 2 pi times 10 kilometers over the fastest one we know of, 1.4 milliseconds or 700 hertz or so, that's about 15% of the speed of light.
And that's faster than the biology program.
Oh. That's right, they don't have 10-kilometer centrifuges. You're so right. I'm going to point that out next time. And so that's the technical term is very fast. And you might wonder, gee, is that a problem? Could you be finding eventually pulsars that violate, special relativity and go faster than the speed of light? And what I would say is this is an active area of research. It's one of the sorts of things that we're actually trying to answer. What is the fastest a neutron star could spin? Because we don't think that we would ever actually violate Einstein's laws, but rather what we'd ultimately be constraining, the periods are very well measured, as I'll explain, but the radii are not. So I say 10 kilometers, it could be 7 kilometers, it could be 13 kilometers. That's an area of active discussion. If we were to find something really, really fast that was pushing the envelope, it would ultimately be constraining the radius of the neutron star and therefore the structure of the neutron star, and ultimately, as I'll explain shortly, the equation of states of very dense matter. So one of the interesting questions we hope to answer is, how fast can a pulsar spin? And in hunting for them, that's one of the things that we have in the back of our minds. So I just want to say very briefly, the fastest pulsar, as I say, was found at this supercomputer. Now is really nothing. It's like sitting in the garbage somewhere. But it was what we used back in 2004, I think, to find the fastest pulsar. This is graduate student Jason Hessel's, whose PhD thesis at McGill was finding this pulsar. And at the time, there was an article in Science about our discovery that was called A Neutron Star in F sharp. And you might wonder, F sharp, that sounds like music. What does that have to do with pulsars? And so this is sort of the brain candy part of the talk, where I just do some fun things with pulsars and explain that pulsars, the fastest pulsars, enter the audio band. And you're talking about hundreds of hertz, and that you can actually take the output from your radio telescope and plug it into amplifier, and you have to do a little massaging of the data, but you can then plug it into a speaker and listen to it. And so, especially for the students who've never heard this sort of thing, I brought with me a few pulsar sounds, where these are really real pulsars, and I'm going to now play for you this pulsar 0329 plus 54, one of the brightest pulsars in the sky that has a spin period of 0.7 seconds. And so what you can hear, you're hearing now individual pulses from the pulsar, once per rotation. In this case, the individual pulses are about the same amplitude, so there's not a lot of pulse-to-pulse modulation.
So the differences in those pulses that we heard, are those real or just noise? Are they real?
In that case, it's real. This is a really, really bright pulsar. Yeah. The next pulsar is another bright pulsar, 0833 minus 45, in the constellation of Vela. And this period is 89 milliseconds, or 11 hertz. And so now it sounds like a little, I won't do that to you. You can hear now strong pulse-to-pulse modulation. And notice sometimes a pulse is missing, but the next pulse always comes back exactly in phase. So one point I'm going to harp on a little later is that pulsars, even though pulse-to-pulse variations exist, probably due to some sort of plasma instability, weather, if you want, on the pulsar, the rotation is extremely steady. These are excellent clocks. The next one is a famous pulsar in the Crab Nebula, pulsar 0531 plus 21, which has a period of 33 milliseconds. I can come back, yes? Yes?
You're saying the cause of it, which is this mechanical rotation, is thought to be completely regular, but then in the sending of the signal, there might be various kinds of instabilities.
Yeah,
or
exactly.
irregularities.
Exactly.
That's the interpretation.
That's what I'm saying. And so I can say, the rotation is extremely steady for many of these objects, not for all. We do see clear what appear to be clear rotational anomalies in some of them, and that it seems to be tied with youth. The youngest pulsars can be extremely noisy. The oldest pulsars are really excellent clocks, very steady spin down. But the intensity of the radiation does fluctuate, even if the time is between them. So the Crab pulsar, 33 milliseconds, and your ear might be having trouble hearing the individual pulses because they're sort of coming so close together. It's kind of an irritating sound. It'll stop. And I should say this is a simulation. So, oopsie. If that is a simulation, because the radio noise from the Crab Nebula itself, which is a famous supernova remnant, a remnant of an explosion of a massive star, the radio noise from that direction is so bright that you can't hear the pulsar over it. So in that case, we had to simulate it. In the last case, it's actually also a simulation, a millisecond pulsar. This one is the second fastest one. It has a spin period of 1.5 milliseconds. And now you hear why the science paper was talking about a neutron star in F sharp. You can clearly hear this is an audio signal. This is not, in the language of music, this is not a pure tone. It has many higher harmonics. That's because these pulses are very narrow. They're beamed. And so in this case, it's almost a pure tone. It's actually kind of a broad pulsar. It's really nice. Sorry. Did you say you want me to do it again, Andre? Okay. Anyway, so why are these objects so interesting? So now just to get back to the physics instead of the fun. Neutron stars in general embody physics of the extreme. So extremes of gravity, where they have gravitational redshifts on the order of 0.3, so they're not quite black holes, but they're in that regime. Densities, where we believe at the centers of neutron stars it's 10 times nuclear density. They have extremes of magnetic field, where we believe the surface magnetic fields on neutron stars are typically 10 to the 12 Gauss, and in some cases as high as 10 to the 15 Gauss. These are the highest magnetic fields known in the universe. And extremes of dynamics, as I'll say, we often find these objects, well, not often, but we occasionally find these objects in binary systems with other stars where the binary is highly relativistic, so that Newton's equations of motion rapidly break down. So they embody all of these physics of the extreme, and yet are very observable, and observable in kind of charming ways. So in a way, their physics dreams come true. Now, I said before that pulsars are excellent clocks, that the pulses come at very regular times, and I just want to emphasize this point because it's important for understanding the motivation for finding these objects. This is the pulse period of pulsar 1937 plus 21. On a specific day, this is the modified Julian day, on this day, the pulse period you can see here to 15 significant digits, where this number in parentheses is the uncertainty in the last digit. So some pulsars, not all pulsars, but some pulsars are extremely stable rotators where, observed over many, many years, we can measure with great significance, so parts in 10 to the 15, the pulse period. So that's very important because you're going to understand this is why there's such wonderful dynamical laboratories for studying binary motion and testing general relativity. And pulsars as clocks when I say a part in 10 to the 15, that's comparable to the sorts of stabilities that we see in the world's best atomic time standards. So that I can't ever say, or it's hard to say at the moment, that pulsar's stability exceeds the best atomic clocks. It's hard to know if you just have one clock which is better. But we know they're at least comparable to it.
Could I interrupt with a naive question? You said very young pulsars sometimes are not so regular.
That's right, yeah.
Should I disbelieve angular momentum conservation, or how should I think of it?
Yeah. So, we don't think angular momentum conservation is violated. We think that there's different reasons why you might expect some sort of event, some torques. Now, the torques on the neutron star, these are very low levels. So, for example, there's one phenomenon in neutron stars called glitches. So some of you, I know, are very familiar with glitches. I know we have Mal Ruderman, and they hear there's a lot about glitches, where the neutron star, especially young ones like the crab pulsar, will suddenly begin to spin faster by a part in 10 to the 6th, the spin period. So in that case, we think it has to do with the fact that there could be fluid inside the neutron star that's rotating a little bit faster than the crust. And if that angular momentum can be transferred to the crust suddenly, then you can observe a slight spin up. So you could ask the question, why should the fluid inside the crust be spinning fast? Why should the fluid inside the neutron star be spinning faster? There's good arguments for why you would expect that sort of thing. Basically, I said they're very magnetized. The magnetic field breaks the exterior of the star. It doesn't necessarily couple to a fluid component. So that's one example of where where you might question angular momentum conservation, but we don't think that's violated. In other cases, we don't really understand the nature of some of these. We call it timing noise. When we don't understand something, we call it noise. We see that there are these rotational instabilities at a very low level, and really their origin isn't very well understood. But we don't. I mean, it's probably it could be a plasma effect. When we time them, we're assuming that the radiation pattern is fixed with respect to the surface of the star. That could wander a little bit. That could be a bit of a problem. But it's a very good question. So I said that these objects are really, really regular rotators, but actually that's not exactly true. They are all slowing down with time. So when I say that they're excellent clocks, you have to remove that slowdown before you can. Generally speaking, it's a linear slowdown. So we characterize any one pulsar by its period and its period derivative, P-Dot. And so the period is always increasing with time, and almost always, but not always, the evolution of the period with time is just a simple linear trend. So P plus P-Dot times time. And just from measuring P and P-Dot, we can actually infer a lot of interesting physics about the neutron star. So from the period and the period derivative, we can, for example, infer the surface dipolar component of the magnetic field under some simplifying assumptions. For example, that it is a dipolar field and that it's rotating in a vacuum. And so, for example, if you it's a simple exercise, you take the Larmor formula for the emission of radiation from a magnetic dipole that's rotating, you can derive that the magnetic field, or at least the dipolar component magnetic field at the surface, is this function of P and P dot, goes like square root of P and P dot, with constants here, where I is the moment of inertia of the neutron star, which for a 10-kilometer radius and a mass of about 1.4 solar masses is something like 10 to the 45 grams centimeter squared, with a radius in here. So you get this constant out here times the square root of P dot, and if you plug all this in, you get this expression over here. So basically the main point of the slide is to say that if you can measure P and P dot, then you can infer, or you get an estimate for the surface dipolar magnetic field strength of the neutron star. And then another quantity that you can estimate is the age of the pulsar. This is the spin-down age. We call it the characteristic age because we don't think it's always exactly the true age of the pulsar. This is assuming that it's born spinning much faster than we observe it today, which may or may not be true. In some cases it is, in some cases it isn't. And it also assumes that it's spinning down again due to vacuum dipole breaking. And under these two assumptions, you can estimate the age of a pulsar to be p divided by P-Dot, and there's this arcane factor of 2. Why is the factor of 2 there? I could explain, but it's not really germane to what I want to get at today. So the main point is that from P and P-Dot, we get an estimate of the magnetic field and of the age of the pulsar. And so now this is a very famous plot that if you go to any radio pulsar conference, you'll see over and over and over again. This is spin period on this axis on a log scale, so varying from a millisecond over here to about 10 seconds. And this is period derivative on this axis going from, you see, 10 to the minus 20 seconds per second up to 10 to the minus 10 seconds per second. And there's one dot here for every radio pulsar that we know. So there's about 2,300 dots here. So the red ones, these are the regular radio pulsars. The biggest swarm that we know of sits at periods of a few hundred milliseconds. Okay. And just notice these lines this line over here labeled 10 to the 12 Gauss. These are lines of constant surface dipolar magnetic field using that formula I just showed you. So this is a line in log space of a constant P and P dot. So this is, a constant magnetic field. So you can see the typical pulsar has a surface magnetic field inferred from that formula of about 10 to the 12 Gauss. There's all sorts of, and also these dotted lines, those are lines of constant characteristic age. You can see this dotted line here at 10,000 years. These are pulsars that are about 10,000 years old as estimated from P over 2 P dot. So a few things to notice. My pointer's gone. The points up here that are surrounded by stars, those are the youngest pulsars in the population, the ones that you're asking about that suffer a lot of timing noise. The stars represent objects that are in supernova remnants, that are in remnants of exploded stars, and we expect only the youngest radio pulsars to be in supernova remnants, because the supernova remnants of exploded stars dissipate very rapidly on timescales of 10,000 years. So you expect all neutron stars to be born in supernova, but only the youngest ones will be found in remnants, and indeed that is what we see. And then another population of pulsars I want to draw your attention to are the ones with little blue circles around them. These are all the binary pulsars. So each red dot with a circle around it has a binary, that's a pulsar with a binary companion, a second star in its orbit. And what you could see is the binary pulsars tend to cluster over here, typically at the very short spin periods. Those are the millisecond pulsars, the pulsars that are rotating every few milliseconds. And if you notice, millisecond pulsars are almost all with binary companions, whereas the slow pulsars, very few, here's a couple, 1, 2, that have binary companions, and we don't think that's a coincidence. So we think that pulsars are born spinning fairly rapidly, and then they slow down due to magnetic braking. But the lucky few that in their supernova explosion do not get rid of their binary companion, since after all, most stars start out in binaries. If you have a massive star, typically it's going to be in a binary system. When that star explodes to form the neutron star, usually that binary is disrupted. One star flies away, they're no longer bound. In the few cases where the binary remains after the supernova explosion, that binary pulsar then, although the pulsar will typically evolve along a line of constant magnetic field, it'll slow down with time. We believe that the reason you find all these millisecond pulsars down here with very, very long characteristic ages, they're not labeled yet, 10 to the 8 years, billion-year-old objects, is because that binary companion has recycled them, has taken the pulsar from, we think what happens to these pulsars, they evolve here and eventually just shut off. The radio mechanism shuts off. But some pulsars get a new lease on life. They get recycled by accreting material from the binary companion, which spins them up to very high spin rates, and then they can live forever. And so I'm going to talk a little bit more about that process. But first, you might wonder how we know pulsars are in binary systems. How can I be so sure when a pulsar is in a binary? And it's very easy. Because you know that, of course, an object, any wave that's moving suffers a Doppler shift relative to an observer. The radial motion causes, blue shifting and a red shifting. So when the star is moving away from you in the binary, the light from its surface is red shifted. When it's moving towards you, it's blue shifted. And so for regular stars, you infer that by looking at the absorption lines in their spectra, and you see those absorption lines moving as the star moves towards you and away from you. In a pulsar, it's the pulse period itself that's Doppler shifted. So we see the period actually getting longer as the pulsar is moving away from you, getting shorter as it's coming towards you. And because pulsars are such fantastic clocks, where for the typical pulsar you can measure the period to a part in 10 to the 10, and for the best ones a part to 10 to the 15, we can measure that binary motion with exquisite precision. So just for example, here's a nice circular binary orbit where you can see the pulse periods with the error bars included. Okay, so there's no question when a pulsar is in a binary, and actually my eagle eye says this is a lousy fit to these data. We really should the periods off there. But in any case, you can see in this case the pulse period is varying itself sinusoidally, and that's because it's in a circular orbit. Sometimes you find binary pulsars in eccentric orbits, and then it can look something like this. This is an eccentric binary orbit, very high eccentricity, and again, the data points are there with error bars. So when a pulsar is in a binary, it's really screamingly obvious. And not only that, you can easily detect deviations from your model. Now, I said these binary pulsars, their progenitors, when you see a pulsar with a binary, especially a millisecond pulsar, their progenitors were accreting neutron stars. So any radio pulsar with a binary companion today, or almost anyone, you have the neutron star was there before, but prior to before that neutron star turned back on as a radio pulsar, the star, its companion star, in this case the cartoon shows a white dwarf, but it doesn't have to be. If it overflows its Roche lobe, it can dump matter onto the neutron star. And as that matter falls onto the neutron star, its specific angular momentum can be high enough that the pulsar can spin up. And during this phase, as matter is falling onto the neutron star, we can observe these systems as bright X-ray sources, X-ray binaries. And we know of many dozens of these objects in the sky. So that's a whole other field. You could have talks on X-ray binaries. In any case, in that process, the neutron star can be spun up to millisecond periods. And at the same time, their magnetic fields can get quenched by that material due to physics that it's not fully agreed upon, but at least we know that observationally has to happen. And so these millisecond pulsars, what makes them, what creates a millisecond pulsar? As I said, you start, you require recycling by mass transfer from a binary companion. And in the process, it spins up the neutron star and quenches the magnetic field. So these millisecond pulsars can end up living forever because then they slow down only very, very slowly. So millisecond pulsars typically are very old objects because once they're recycled, they live forever. And typically they're distributed isotropically, or not quite isotropically, but almost isotropically on the sky. Whereas most pulsars are confined to the galactic plane where they were born in supernova explosions, millisecond pulsars are so old, billions of years old, that they've had lots of time to drift away from the galactic plane, and we tend to see a very broad distribution of them on the sky. And they typically are in circular binary orbits with degenerate companions, typically white dwarfs. And so there's a very strong evolutionary relationship predicted between these X-ray binaries. This is an example, low-mass X-ray binaries and millisecond pulsars. This is sort of the textbook view, and this is from a nice review article by Duncan Lorimer, where he shows you how millisecond pulsars can be formed. If you start out with two massive stars, one is more massive than the other, it dies first, whoomph, that's the supernova that produces a neutron star. In most cases, as I said, that binary disrupts and you end up with a pulsar and a runaway star never to be together again. But in the cases where the binary survives, you have the pulsar and the companion. Eventually that companion grows to its giant phase, dumps matter onto the neutron star. And in the case where this star is not too massive, that's where you can end up with a circular millisecond pulsar white dwarf binary. In other cases, if the star is sufficiently massive, then you go along this track, That star eventually has a supernova. Sometimes that binary disrupts, but when it survives, you get a double neutron star system. There's 2 neutron stars, and that's like the Hulse-Taylor pulsar. They're typically relativistic and quite interesting to study. So the vast majority of binary pulsar systems are either double neutron star binaries or millisecond pulsar white dwarf binaries, or at least this picture is what we believed for many, many years. And what I'm going to show you is in the pulsar surveys that I'm getting to, we found objects that really don't agree with this textbook evolutionary explanation of the relationship between X-ray binary systems and millisecond pulsars. So just to come back to this point, pulsars are fascinating physics laboratories. They can allow us to study the equation of state of ultra-dense matter. They're very dense objects. One way we can study that is by measuring masses of neutron stars. And there's once you have these wonderful binary systems, particularly the relativistic ones, you can use relativistic effects to measure the masses in the system with great precision, sometimes to a part in 1,000. So we can measure masses of neutron stars, and the different models for equations of state of ultra-dense matter predict different maximum masses for neutron stars. So let me show you a plot here. It's about the equation of states of neutron star matter. Like I said, there's a lot known, or a lot believed we know about the structure of the neutron star, but at the core, where the density gets really high, there's a big question mark there because the equation of state of this dense matter is really not known. And this is a plot that shows this mass-radius relationship for neutron stars. Here's mass on this axis and radius. And each of these curves is a different possible equation of state for very dense matter. And so what you can see, many of them have this structure where they have a very sharp rise, so in fact, almost independent of mass. They're all at very similar radii, but they all predict a fall-off, a maximum mass of the neutron star. So for any one of these models, a neutron star has to sit on one of these curves. So you could see by, for example, measuring the mass of a neutron star, you see my pointer's now. Yeah, there it is. No, it's not. I'll use the cursor here. But you could see, for example, by measuring masses of neutron stars in relativistic binary systems, here's one that we measured to be 2 solar masses, pulsar 1640. You could see we've ruled out any equation of state that predicts a maximum mass below our measurement. So I mentioned to you one way of constraining equation of state, I said earlier, was to measure ever faster rotations. Oops, I meant to go this way. So so we can constrain the equation of state of ultra-dense matter. There we're doing particle and nuclear physics by studying neutron stars. One way is by measuring maximum masses of neutron stars. And the other is, as I said earlier, measuring really, really fast neutron stars that can also constrain the equation of state, because different equations of state predict different maximum rotation speeds. And then we can also, that's one way that we can use neutron stars for fundamental physics. Another way is by finding them in these relativistic binary systems and then testing, are their orbits well described by general relativity? And of course, there's Nobel Prize in 1993 to Hulse and Taylor who first did this. But there's, that Hulse-Taylor pulsar was wonderful, but we've been finding more and more relativistic systems that can push the limits on general relativity even further. These systems are also wonderful laboratories, like I said, for studying binary evolution, for understanding the relationships between millisecond pulsars and their X-ray binary progenitors.
Is general relativity correct?
So far, it's worked, but the tests of general relativity when Einstein was alive were all in a very weak field regime where perturbations from general relativity would be really small. So now here you're going to strong regimes where you might expect to see something happen. So far everything's worked, but you have to check to see if it. As you go to regimes where the deviation should be really strong, then you have a chance of measuring something different. And of course, there's connections between these topics. So binary evolution predicts we should find radio pulsar black hole binaries. They're predicted that it should be something like for every 2,000 radio pulsars we know of, one should be a pulsar black hole binary. And we're all dying to find it. because if you could find just the right pulsar black hole binary, it would be superb for different tests of general relativity. And there's good arguments why they're going to be hard to find, but we're still hopeful. And there's one other reason that we want to find millisecond pulsars. So I'm still motivating here, but the major reason is that general relativity predicts the existence of gravitational waves. And these waves are still yet undetected. And of course, if you could detect gravitational waves, it could, in principle, revolutionize astronomy, because it would be a new window on dark objects, particularly black holes and in some cases neutron stars. And of course, there's ground-based gravitational wave detectors like LIGO and Virgo that are operating or being continually upgraded, where we hope to detect gravitational waves. There's also proposed space-based gravitational wave detectors like LISA, the Laser Interferometric Space Antenna, which I'm not sure it's going to launch anytime soon, but it's at least envisioned as a potential way of detecting gravitational waves. But pulsars can also be gravitational wave detectors. And this is a very exciting thing where we want to use pulsars as tools to detect gravitational waves via what we call a pulsar timing array, where we hope to detect gravitational waves in the nanohertz regime, so that is with periods of years, using millisecond pulsars. And the idea is that we would want many millisecond pulsars distributed roughly isotropically on the sky, and we would be monitoring them using their great precision as clocks to look for small deviations that could be due to the passage of gravitational waves. Now you might wonder, what sort of gravitational wave sources are there in the nanohertz regime? And the answer is that there are merging galaxies, merging supermassive black holes. So at the center of every galaxy, we believe there's a supermassive black hole. The Milky Way has a supermassive black hole. And we also see on the sky many examples of galaxy mergers, where we see two galaxies that are interacting that we believe will eventually merge. And so supermassive black holes in them would also merge. And this is an example of an optical image of merging galaxies called the MICE. And this is a computer simulation that, is there to show you that it really is reasonable that is a set of merging galaxies, because when you take two, for example, spiral galaxies at just the right angle and rotation speeds, you can reproduce the observed image. So we believe there are merging supermassive black holes all over the universe, and those should be producing gravitational waves, a stochastic background of gravitational waves in the nanohertz regime. So the idea here is that, for example, you have here's two real spiral galaxies, and zooming in, you can see the two supermassive black holes, and the green grid is there to represent space-time, and the ripples are the gravitational waves that they are producing. And this is just one example, but the idea is we're detecting we could detect a single source if it was nearby, but really it's the background of all the merging galaxies throughout the universe. And in this case, you see those galaxies conveniently beam those gravitational waves directly at the Milky Way, which is really handy. Sorry about that. That's not quite right. But back here on Earth, with a really massive radio telescope, we can observe, in this case, one pulsar, and we would see, as the gravitational waves pass, the pulse arrival times being advanced and delayed as the waves pass. And of course, you wouldn't trust one pulsar, because as we said, not all pulsars are perfect clocks. That's why you want an array of them. You want to time many of them at the same time, because you expect very clear angular correlations between these advances of delays on the sky. And just if you're wondering, is that something that's like rivaling LIGO or LISA, it's very complementary. So this is a plot of gravitational wave strain versus frequency of gravitational waves. You could see LIGO operates in this part of the gravitational wave spectrum over here, where these are galactic black hole mergers or things like that, or neutron star mergers. Sorry, I don't mean galactic. I mean extragalactic, but galactic scale, so few solar mass objects merging. Whereas the pulsar timing arrays are way over here, where we're talking about supermassive black hole mergers, and these are the sorts of sensitivities we get. And you can see for many of the current sensitivities, we're actually in territory where we could almost detect, at least at the predicted rates of supermassive black hole mergers. So we now are already doing this pulsar timing array with about a couple dozen pulsars, and we are close, well, at least given models for the amplitude and the spectrum of gravitational waves from supermassive black hole mergers. We have the potential that we could detect these soon. Yeah.
What's the spike in the sensitivity?
Yeah. So that's a year. So we don't have a lot of sensitivity at a year because the Earth is moving around the sun, and we use that effect to measure the pulse position on the sky. So a year and its harmonics, we don't have a lot of sensitivity to. So why do we want more millisecond pulsars? Well, for all the reasons I've told you, we want to find the fastest ones, we want to find the most massive ones, we want to study binary evolution, but also we want to detect gravitational waves. And what this plot is showing you how much the pulsar timing array's sensitivity to gravitational waves improves when you add pulsars to your timing array. So if you look at the black curves over here, this black line is the sensitivity. So this is the significance of a detection of gravitational waves as a function of the gravitational wave characteristic amplitude. So the black line is for 20 pulsars in your array, timed for 5 years. This black line is for 20 pulsars timed for 10 years, and you can see your significance, of course, for a fixed amplitude goes up. And this one is if you time them for 20 years. So you have to watch for a long time, and your sensitivity improves. But now consider the red lines. The red lines are for if you have 50 pulsars in your timing array, timed for 5, 10, and 20 years. And you can see that for a fixed amount of time, you win big by adding more pulsars to your array. And so the blue lines are actually for 200 pulsars. And my goodness, you can do a really good job when you have lots of these millisecond pulsars. So what we want to do is find more millisecond pulsars, and not just any ones. We want the really stable ones to add to our pulsar timing array to increase sensitivity to gravitational waves.
But what's the actual expected amplitude on Earth?
Oh, that's in, yeah. So actually, how do you compare? So that's for a standard prediction. So the significance in this case.
Significance. Okay.
Yeah.
Okay.
For your number of pulsars, are you limited by the numbers of millisecond pulsars you know, or are you limited also by the time you get on various telescopes?
Yeah. So we think we're sure we're detecting a tiny fraction of all the pulsars in the galaxy. And we know, and I'm going to tell you, we're doing surveys, and we're finding tons of new millisecond pulsars. So these surveys are churning out millisecond pulsars, many of which are surprisingly bright. They weren't found in previous surveys because previous surveys didn't have the sort of computing power we have today. This whole field is not so much driven, yes, telescope time matters, but computing power and ability to record fast sample digitized data and to search it efficiently, that is what is driving the field. So as computers get faster, we find more pulsars.
Don't you already have 20 pulsars?
Yeah, but 20 is...
You have discovered the gravitational wave.
Yeah, so recent paper by McWilliams, Ostreicher, and Pretorius says that yes, we're almost at the regime. In the next 5 years, we're going to detect them.
Even with current samples?
Even with current samples. There's other papers, Susanna is somebody who's done a lot of work on this, who thinks that their estimate for the gravitational background was a little optimistic, and that it's going to take us, with the current number of pulsars, maybe another decade. Maybe it could be 2 decades. But by adding more pulsars, we should be able to find it faster. That's why, and this is the real reason I find this. This is why I want to find pulsars.
Work, right?
It's a lot of work. Yeah.
No, it's going to work no matter what.
Oh, it's well, okay. So we can talk about it. Yeah. So, holy cow. Yeah. So it's going to work. Well, so there's debate about that. Some people are not sure that supermassive black holes in the end merge. There's something called the final parsec problem, where people who simulate supermassive black hole mergers can't actually get them to merge. So there's different gas dynamics and dynamics of how stars interact with these merging objects Because I showed you a cartoon where the two supermassive black holes are interacting with nothing else around them. If you add in all the other stuff that you think should be there, they don't necessarily always merge. So Scott Tremaine, for example, is somebody who's not convinced these things ever merge. So even though you see them on the sky looking like they're merging, at the final parsec, right where it accounts for pulsar timing arrays, they may never actually merge. So that's actually a problem. So it's true, these pulsar timing arrays may never see anything. But at least then, I think if we didn't see anything eventually, then we would say, okay, they don't merge. That'd be sad. But it would be an astrophysical statement. So I don't have a lot of time, so I'm going to tell you about how we find pulsars, and then I'll just very quickly survey some of the discoveries we found. We find pulsars by defining a survey area. We point with big radio telescopes, and for each pointing, we record very fast samples, frequency channelized data. We remove RFI, that's radio frequency interference. And as I say, we de-disperse at trial dispersion measures. I don't have too much time to talk about that, but basically pulsars are dispersed by the ionized component of the interstellar medium. And this smears out pulses terribly. So that actually adds huge amounts to our computation time. So not only do we have to do these fast Fourier transforms of very long data sets, but we have to do also removal of dispersion measure effects, which is very computationally expensive. So all of this is a high-performance computing application. And I'm going to skip that slide. And I'll just also show you another problem, especially for millisecond pulsars, which you might not appreciate because you think a periodic signal, Fourier transform, it's easy. It's not easy if the pulsar is in a short binary system, because over the course of your observation, the period could have changed due to Doppler effect. So this is an example of a pulsar. Here's the Fourier signal. You see the power, and it's normalized to be unity here. This is an isolated pulsar. If you now put it in a binary system, so here in this case I put it in I stole this plot from Scott Ransom, my colleague. You put it in a 1-day orbital period. This is a 3 millisecond pulsar, and you do a 2-hour observation of it. You see all the power, now the maximum is down at a few percent of what it would have been if it had been isolated. The power is now spread over many Fourier bins. And so this is a problem with finding binary pulsars. Not only do you have to do this plasma effect removal, this dispersion measure removal that I didn't have time to talk about, not only do you have to do giant Fourier transforms, but you also have to do what we call acceleration searches, where you try and search in period derivative space for linear trends in the period due to the motion of the binary. And that you have to do for thousands and thousands of positions on the sky. This is why it's HPC, high-performance computing. So I'll just mention very quickly at the end a couple of pulsar surveys. This is a survey that we're doing with the Arecibo telescope in Puerto Rico. This is the largest radio telescope in the world, 300-meter aperture. We're searching at a center frequency of 1.4 gigahertz, bandwidth 350 megahertz. For this whole survey, we're collecting about a petabyte of data. So that's a lot of data. We're doing another, in this case, we're only surveying the galactic plane for pulsars. The field of view of the telescope is really small, so it's hard to do an all-sky survey in that case. But we are doing an all-sky survey with the Green Bank telescope. That's the 100-meter aperture telescope in West Virginia. In this case, at a lower radio frequency, 350 megahertz, and that's about half of a petabyte of data. And so this is a supercomputer application. We're doing this processing at a supercomputer at McGill University, thanks to Calcul Quebec and Compute Canada. And I'll just mention that PALFA, the Arecibo survey, is finding some of the most distant millisecond pulsars known. So this survey is opening up the galaxy. We're able to find these pulsars thanks to PALFA in a far greater volume of the galaxy than we have before. So this is now looking down on the galactic plane. Here's the sun. Here's the galactic center. You see the spiral arm structure, and you can see each dot is a pulsar. And these blue, this is the region of the galactic plane that Arecibo can see. These are all new millisecond pulsars over here that simply were not detectable before, thanks to the sensitivity of Arecibo. I want to highlight one particularly interesting source from this survey, which is pulsar 1903 plus 0327, which is an eccentric millisecond pulsar companion, eccentricity 0.4, orbits with a non-degenerate companion. And this is sort of the opposite of what I told you earlier about what happens to recycled pulsars, that they end up either in double neutron star binaries or in circular white dwarf binaries. In this case, it's, either case is a degenerate companion. Here we found one that we really weren't expecting. It's the first eccentric millisecond pulsar in the galactic disk. And, how do you end up with a pulsar? This is a very bizarre question for binary evolution. You don't expect to see these kind of eccentric MSPs. And to make a long story short, we think this system must have undergone a formation mechanism with a triple system where a different star recycled the pulsar to millisecond periods, and then somehow that triple system, that star must have been unstable, was ejected, and we're just left with a second binary companion that was not responsible for the recycling. And what's also interesting about this system is that there's a relativistic effect in the system where the orbital plane is quite inclined. And so there's an effect called Shapiro delay, named after the Harvard astronomer Erwin Shapiro, where pulses are delayed as they pass through the space-time metric of the companion, which allows us to get a very good measurement of the mass of the companion and the neutron star. And in this case,
you're not talking about Doppler shift here.
No. So
you're talking about a gravitational effect.
Yes, this is a general relativistic gravitational effect. So Doppler shift is just the radial motion. In this case, there's an additional component when the pulsar is very close to being behind the companion, because the companion's space-time is distorted. There's an additional delay in pulse arrival times from the pulsar. And from that delay, it's a very, very strong effect. With orbital phase, we can measure the mass of the neutron star very well. In this case, the mass came out quite high, something like 1.7 solar masses. And I'll just mention very quickly. We found something like, almost 20 millisecond pulsars now with P-alpha. Some of them are good for the galactic, for the pulsar timing arrays. We've since found a second eccentric millisecond pulsar, and we're very excited by that. We think we may have found a new class of millisecond pulsars that forms by a mechanism that is simply was not expected. How much time do I have left?
Well, you started 5 minutes late, so you have.
I'll do 5 minutes. So I'm going to skip over. I'm not going to mention the fast radio burst, guys. So I know some of you would like to hear about that, but I won't tell you about that. Instead, I'll mention very quickly this GBNCC survey, the Green Bank North Celestial Cap Survey, where we're actually surveying now the northern sky, and in fact, we're actually extending down below. This is the pink region is actually the P-alpha survey. That's where Arecibo is surveying. With Green Bank, we're surveying a much greater part of the sky. And here's one of the very interesting sources that we found as part of this survey, very exciting. This is a millisecond pulsar low-mass X-ray binary transition object. So I told you earlier that you can, millisecond pulsars are born from these low-mass X-ray binaries. Well, we found this 1.7 millisecond pulsar at the position of a cataloged low-mass X-ray binary that used to, just 10 years ago, have an accretion disk right there. And so that was very strange to us. How do you find a millisecond pulsar in a place where there was just an accretion disk recently? We expect that accretion disk to have gone away billions of years ago. But what we think was that this is a millisecond pulsar that had just been born, sort of a missing link between the old millisecond pulsars that we've been studying for many years and the low-mass X-ray binaries. So we postulated in this paper that was written by graduate student Ann Archibald in Science, perhaps it's not accreting today, but maybe it'll maybe it'll go back. If it had an accretion disk 10 years ago, that accretion disk, perhaps it could form again. Did we really find it at such a special time in its evolution where it just flipped? And so what was amazing to us is that not long after we published that paper, the pulsar disappeared from the sky. So in June of 2013, the radio pulsar vanished, and at the same time, a coincident Fermi gamma ray source got a factor of 5 brighter. X-ray flux from the source increased by a factor of 20, and we believe that it has gone back to a transition where it now again has an accretion disk, possibly is accreting material. although not in a traditional way, which I can explain. And the question is, will this radio pulsar return to the sky? Will it be spun up slightly by this brief episode of accretion? What will have happened to its spin period? That was quite a surprise to us. And then very briefly, I'll mention this one system we also found with Green Bank, because it's really exciting, 0348. This is a 39 millisecond pulsar in a 2.4-hour orbit. So this is highly relativistic, the second most relativistic system known. This was published by graduate student John Antionitis, also in Science in 2013. In this case, as a white dwarf companion with a mass that's very well determined from its spectrum to be 0.175 solar masses. And here what you can see is, because it's a white dwarf, it has spectral lines that we can measure its radial velocity. So we get the Doppler shift from the pulsar, and we get the Doppler shift from the white dwarf spectral lines. And that's what this is showing you. This is the radial velocity. The green is from the pulsar, which is extremely precise, of course. And the blue line is the fit to the data from the white dwarf. So we actually have two lines there. We have a double line spectroscopic binary. That is, we immediately know the mass ratio of the system, because it's the ratio of the amplitude of these curves. So that mass ratio, Q, is 11.7. And then because we know the mass ratio, and from white dwarf modeling we know the mass of the white dwarf so precisely, we know what the neutron star mass is. And it's the most massive neutron star yet known, 2 solar masses. And this is, of course, as I said, very relevant to the equation of state. It rules out many equations. It's inconsistent with previously proposed equations of state for dense matter. And also, so this is like a twofer. We found this massive neutron star in a highly relativistic orbit. That's a first. So the first massive neutron star in a highly relativistic orbit, you can now test GR in new regimes. And I'm running over, so I'm going to say very quickly just that in some alternative theories of gravity, you can have dipolar gravitational radiation. So in Einstein's theory, the radiation only comes in a time variable quadrupole moment. For tensor scalar theories, that is where you have a tensor and a scalar, you get dipolar radiation damping as well. And from studying this new binary pulsar consisting of a massive neutron star and a white dwarf relativistic system, we can set limits on, for example, the component of any orbital decay due to emission of gravitational radiation that sets limits on post-Einsteinian parameters. So parameters that would parameterize any scalar theory, any scalar component to a tensor theory of gravity. And so we have this upper limit on these parameters, which I'm not going to get. I don't want to get too. It'll take me 5 minutes to explain, but I don't have those 5 minutes. What I really want to convey is that from that model, from that upper limit, we can now help our compatriots at LIGO who are trying to detect merging neutron stars, where previously these sorts of post-Newtonian, post-Keplerian, post-Einsteinian effects, where deviations from general relativity would matter for 1.4 solar mass neutron stars. There's good limits on those already. But what if you had a more massive neutron star and you were trying to detect through gravitational waves the in-spiral of a merging system? In GR, for example, this is the sort of waveform that LIGO would expect to have, whereas in a tensor scalar theory, the merger happens way faster because of the rapid emission of gravitational waves, much more rapid because it goes with a dipole. And so if you don't know if there's a tensor scalar theory versus general relativity, you cannot detect a massive neutron star merger with LIGO. You just wouldn't be able to do it because you need a template to dig out in the noise of LIGO. And so now that we have this system, we can actually set limits on the number of cycles that can possibly deviate from general relativity. And we know that this is sort of complicated, but the point is that from 0348 found in the GBNCC survey, we can set a limit of this red line on these parameters, on these tensor scalar theory parameters, that says that almost certainly the number of cycles in the merger waveform will deviate from GR by less than one cycle. So that's very encouraging for the people at LIGO. They should be able to find massive neutron star mergers as well. So that's another example of the sort of science we do. And I'll just say very quickly, we have lots of new millisecond pulsars that our surveys are finding. This is just another sample of something like 20 of these, and you see, overall, we want to find these millisecond pulsars to put them in the pulsar timing array, but then we find these really interesting individual sources, each of which has a whole science story to tell, and I just don't have time to tell you that each one. It would take too long. But that is, the overall picture of why we're searching for millisecond pulsars. And so I'm just going to skip all this chime stuff because I knew I wouldn't have time and get to my conclusions. So, pulsar surveys are important for many different reasons. As I hope I've motivated to explain, PALFA and the GBT surveys have been extremely fruitful to find new pulsars for pulsar timing arrays and a whole array of interesting and unexpected binary pulsars, including eccentric millisecond pulsars, missing links between different populations, and interesting tests of general relativity. And as I hope I showed you, we're still finding them, and there's lots more to come. Maybe we'll eventually find sub-millisecond pulsars or that pulsar black hole binary we're dying for. And I didn't have time to talk about that, so I'll stop. Thank you very much.
I have a question for the radio pulsar that disappeared.
Yeah.
So X-ray binaries will soft and brighten all the time, so that part's not surprising. So what's the mechanism, what's the interpretation for the radio pulse disappearing?
Yeah. So there's two things. One is that, I didn't have time to say it, but when the radio pulsar was on, it was eclipsed for something like half of the orbit, depending on what radio frequency you were looking at. And so we know, even when the radio pulsar was on, there was a lot of plasma in the system. And so there's two possibilities for why the radio pulsars has disappeared. One is that, well, there's tons more plasma there, and they're just dispersed or scattered away. So the radio pulsar could still be on in that case, and just we can't detect the pulsations. Another possibility is that there is material that is getting down to the surface of the neutron star, in which case we expect the radio pulsation mechanism to be quenched. So which of those two possibilities, I don't think it's 100% clear, but there's a lot of, it's not 100% clear, but it's one of those two.
So I was intrigued early on, you talked about them changing their angular momentum through their spinning speeds was change of angular momentum.
Oh yeah, glitches, yeah.
Is there, neutron stars are essentially superfluids, I guess.
Well, they have a superfluid component. It's not entirely
so
superfluid.
Is there any, do people actually ever try and probe the properties, material properties of the neutron stars by looking at things like these glitches, and or are there other ways of doing that? I mean, I'm a condensed matter physicist.
Yeah.
So I want to know if there are ways of doing condensed matter physics on these things.
Sure. So I think it's actually condensed matter physicists who put forth some of the theories that really we still discuss in the literature today for pulsar glitches, where we think, for example, you have the superfluid where the angular momentum in the superfluid is quantized in these vortex lines. And I feel a little bit awkward telling you this with Mal Ruderman sitting right there, and he's a real expert at this, but we think that the angular momentum is quantized in these vortex lines, and as the neutron star spins down, the density of vortex lines has to decrease, and so these lines move outward, but if they get stuck or pinned on these nuclei in the crust, then they can't move outward, and that's the mechanism by which the superfluid does not spin down, whereas the crust does. And so every now and again, if these vortex lines, if there's too big a force on them, they can move out, and that's how angular momentum could be transferred. And so there is a literature on this. I'm a humble observer, and I think there's actually some interesting problems with that whole picture, which really forms the basis of the literature for glitches. So, for example, so I think there's lots of work to be done on this. This is why I would love to talk to you about it. There's a prediction there that glitches should be rare in very hot objects, for example. And that has to do with the pinning force as a function. It's a very sensitive function of temperature. So if something's very high, then they shouldn't pin so easily. So you shouldn't have these glitches as often. Whereas in other work that I haven't discussed, we found some really hot neutron stars, what we think are really hot, that glitch all the time. And so that doesn't agree with basic. So I'm telling you this stuff, and I'm sort of, in my mind, I'm not 100% sure it's right. But there's a vast literature that does discuss it.
I'm going to go with Peter, because I don't know what you're going to say.
Another naive question, very far from the large questions you're asking. In your population of binaries, is there any population of both of the binary members are pulsars, and you can see both of them?
Yes. Yes. So there's there was one case. So there's a case where there was a case where there were two pulsars, and I mentioned this 0348 was the second most relativistic binary known. The first most relativistic binary one is that one, the double pulsar. 2.4-hour orbit, where one pulsar was 22 milliseconds and the other pulsar was something like 3 seconds. So clearly one recycled, one not recycled. And there's a whole bunch, many papers on this object. It's fascinating reading, and I've written a few of them myself. An amazing system, not merely because both of the neutron stars turn on as pulsars, but also through some miracle that I can only think a deity must be responsible for. The binary orbit is within a degree of being exactly edge-on. So you see it's something like, it's been measured at 89.9 or 89.7 degrees or something like that. And so in that system, one pulsar actually eclipses the other pulsar for 30 seconds out of every 2.4-hour orbit. And I'll just say this, that I said it was a double pulsar system because of general relativistic precession, we believe. One of the pulsar's beams has precessed out of our line of sight. And so one of those pulsars is no longer visible in the sky. And it was painful because you could see it fading over something like 5 years. And everybody was saying, is it going to disappear? Is it going to disappear? And it did. And so now there's only one pulsar there.
When's it coming
So
back?
what was this?
Right. So when you said, when's it coming back? So you have to then model what is the shape of the beam, and if you think you know so you believe general relativity, you can. The real uncertainty is in the shape of the pulsar beam. And so there's estimates that it should come back, in decades to centuries timescale. So, I won't be there, but one of your descendants will be there.
All right, well, you can ask more questions to Professor Kaspi upstairs. There'll be refreshments. So